Welcome to our last tutorial of the term, tutorial 4. And the plan is, of course, to continue talking about transistors. Up until now, we have seen the basic characteristics of the BJT and MOSFET, and in each case of two types, NPN, PNP for the BJT, and N-channel and P-channel for the MOSFET. And I hope I was able to convey the key message that as far as circuit level behavior was concerned, the IV characteristics were concerned, there were great similarities. And so you would expect that there are many types of circuits that you could build with one or the other. And of course, if one, when one gets to more advanced circuit design, the details of the differences of these two become important, and then there will be clear choices in some cases. But in terms of basic functionalities, there are many things that you could do with both in very similar manners. We also have seen a couple of examples, or a few examples, of how to use them in circuits, how to get, for instance, amplification. What I'd like to do for today is to look at a few other examples in which we have one or more transistors in basically a DC steady state, where we put the transistor together with a few resistors and see which part of the IV characteristics, if you want, the transistor ends up in, and what kind of functionality it allows us to achieve with that circuit. Okay, and we won't have time, of course, to do all circuits with all four types of transistors. So we'll do some with one and some with the other. And hopefully today will serve as, if you want, an opportunity to get a little used to solving basic circuits with transistors, so that then tomorrow in the lecture we can continue getting into some more specific topics. Okay, anything you guys would like to ask before I start? If not, maybe I'll just invite you to take 30 seconds and try to remember what the current voltage characteristics of any of these four transistors looked like. Who remembers that? Well, this is really the key thing. Even without drawing one of these transistors, this is what I'd like to emphasize, that you have essentially a device that has, if you want, an input and an output. It's a three-terminal device, so if you choose one of the terminals as a common terminal, then you can define an input and an output voltage and current. So at an abstract level, you're thinking about something that's inside the box, right? And it has an input side and an output side. And of course, it's actually a three-terminal device. So inside, this is connected, right? So, but same thing, you can think of it like this, right? This is all the same. So for instance, in the case of the BJT, this would be your base emitter voltage for an NPN BJT, and this could be your collector emitter voltage, right? And more specifically, this is what we are talking about. Base emitter voltage versus the collector emitter voltage. And of course, you have the current that goes in on either side, right? So that's your base current here, and collector current there. Okay. So this is what we are dealing with. And at a very abstract level, so now I'll erase this because I don't want to be bound to a particular type of transistor at this point. This was just to remind you. At a very abstract level, or high level, we are talking about a current on the output side or on one side whose value does not depend on the voltage on that side. And again, here I've taken the right-hand side to be the output, which is very commonly the case. So a current whose value does not depend on that voltage, but can be controlled, the level can be controlled by a voltage or current at the input. So for instance, in the case of that BJT, it would be the base emitter voltage, or you could think of it as the base current that determines which one of these lines you are, which one of the values of current on this axis you get on the output side. Not the voltage of the output side itself. And this is a current source, and it's a current source that's controlled by some other signal somewhere else, a voltage or current somewhere else. And of course, we saw that this works in a range of the output voltage. Otherwise, you would reach a decline. And the details of the curves, the actual equations were different for the BJT and MOSFET, but the general shape of the behavior had a lot of similarity. Okay. So we want to see how this plays out in circuits and how to go about, well, first of all, solving some circuits with them, and then hopefully from that gaining some insight and being able to then design other circuits. So let's start with an example. And this is really ultimately all we are doing. We are solving examples. Some of them famous examples, but examples nonetheless. This is an NPN bipolar junction transistor. I have connected a 1 kilo ohm resistor in its emitter, a 10 kilo ohm resistor in its collector. Up here, I have connected it to a 20 volt supply. This is all the same, 20 volt supply. Okay, and on this side, I have put a 20 kilo ohm resistor here and a 10 kilo ohm resistor here. Solve this circuit, meaning find the voltages and currents. Now I'll say that this transistor is a pretty standard looking transistor. It has a beta of 100, pretty ordinary in terms of its parameters. Let's try together. One thing I'm hoping that we will see throughout the examples today is that, and I'll remind us that, of course, like any other circuit, you put in your KVLs and KCLs and element relationships, and you will get the answer. But of course, the element relationships are kind of a little more elaborate than something like a simple resistor. And there are different regions of operation. Is the transistor on? Is it active? Is it saturated? And so it helps to approach these problems with a mindset or goal of trying to gain insight into the operation. And that usually comes with trying to take a look from a little farther away before diving deep in, right? If I look at this particular circuit, first of all, does this look familiar? Does this look like something that you have seen maybe before? Yeah? Well, I think it was maybe last time or maybe the previous lecture. where we looked at a circuit that had a transistor in this configuration. You had a resistor in the collector, another one in the emitter, and there was an input voltage applied to its base, right? And we plotted the current voltage characteristics, or rather the output voltage versus the input voltage for that. And we saw how, depending on the value of the input voltage, the transistor could be active or saturated, right? This is very similar to that, except that we haven't connected a voltage source directly to the input. I have put two resistors like that are not in series, but they're connected to the base. Now, if you think about this from a very sort of engineering approximation type of approach, if you're dealing with a transistor, what is the first, with a BJT like this, if you want to simplify things for yourself, what is one of those things that you might be thinking about neglecting? Something that's a lot smaller than some other things. The base current, right? Now, you have to be very careful about that, right? But it's something that you can start with. Think about whether that might potentially be applicable and useful. So let me start my analysis by taking that view that, you know, I have a base current there, and that is what is preventing those two resistors from being in series, right? If I disconnected this wire there, now those two resistors are in series, right? What would the voltage be at this node? Yeah, so 6.6 volts approximately, right? Let's say 6.66 volts. You have a simple voltage division there, right? Of course, things are not that simple because you have this connection, which means you have this base current, which ruins this whole thing, you might say. And then, well, how do I know that base current? Well, the base current, I could think of it as maybe 100 times smaller than the collector current. But how do I know the collector current? Well, that's more or less the same as the emitter current. Maybe 0.99 times the emitter current. Now, how do I know the emitter current? Well, it would be very helpful if I knew this voltage right here, right? The emitter voltage. Then I could just divide it by 1 kilo ohm and get that current. And how would I know this voltage? Well, you might say for an ordinary transistor, if things are on, the base voltage is about 0.7 volts above the emitter voltage, right? VBE, that input diode is about 0.7 volts forward. So if I knew the base voltage, then I could say the emitter voltage is 0.7 volts approximately below that. But the trouble is I don't know the base voltage because that base current ruined that simplicity that allowed me to get that 6.66 volts, right? So if I have the base current, that's not accurate. Now, does that mean that I cannot solve this circuit because I went in a circuit? No, it doesn't, because there's other pieces of information that I do know. But that would require setting up a system of equations, right? And things could be a little messy. Now, sometimes you have to do that. What I'd like to show is that it's helpful to first try to understand the circuit as much as possible without launching into the equations. So what I will do now is, as a first approximation, okay. As a first approximation, I will, for now, neglect the base current. Okay? Assume that it's very small and neglect it. It's purely an assumption that I have not justified yet. If I neglect it for now, if I choose that to make that approximation, then I've got my approximate voltage here, the 6.66 volts. And from that, it follows that this node would be at 0.7 volts below that. How much is that? Approximately 6 volts, right? I'm doing things very approximately. So 0.66 volts below that. Then what is IE? Six milliamps. Then what is IC? Same as IB. IE. 6 milliamps. And finally, this voltage there, what is this node voltage? 20 minus 10K times 6 milli. All right, so I came up with an approximate solution. Now you might say, well, okay, now what is the current in these resistors here, approximately, this current going down here? Well, that was neglecting the base current, those two things being in series, that's 20 over 30, right? So that's 2/3 of a milliamp, approximately 0.66 milliamps. All good? Everyone happy? Think about this outcome. And by the way, what would the base current be? Well, we have assumed that it's approximately 0, but maybe you care to try to come up with a slightly more accurate first order estimation. Is this impossible? Why is that? Yeah, no, you know, it feels kind of a little awkward. Now, we haven't really proven that this is impossible, right? But it certainly doesn't rhyme well, right? Now, imagine if I had changed the parameters a little bit. For instance, if I had changed that 10 kilo ohm resistor at the top to a mega ohm, I would have gotten a very huge negative voltage there. And think about how I could now change that to a giga ohm and you get an enormous negative voltage from this. There's something about it that doesn't seem right. What's happened here? Where have my assumptions gone wrong? So that was one thing that I kind of assumed IB was approximately 0. Let's think about this from the point of view of the transistor. Which mode of operation is the transistor in? Certainly, our assumption has been that it's active, right? The collector and emitter have almost the same current. The base has a current that's 100 times smaller. Was that assumption justified? Has it been validated by the solution? Well, what was the condition for the BJT to be in active mode? Well, first of all, it had to be on. The base emitter voltage had to be 0.7 volts, give or take, right? And I have not violated that. I have a base emitter voltage of 0.66 volts. What was the other condition for being in the active mode? Can scroll up. Say again? the collector emitter voltage had to be, in the case of the BJT, for instance, this had to be, the collector emitter voltage had to be greater than approximately 0.4 volts. What is my collector emitter voltage here? This is most certainly not greater than 0.4 volts, right? This transistor is not in the active mode. And this should be very deeply disturbing, especially if you take the view that this implies that the base collector diode has a forward bias of around 45 volts. Right? That's a very, very harsh thing for a diode. And so imagining that you build a small circuit like this and it imposes such a huge forward on that diode is again, a little hard to reconcile with what you would expect. So what happened there? What should my next step be? Was the problem the fact that I simplified things? Well, I think it's both of those things. First of all, I did an approximate solution. Who knows if it was correct? Second, or if the approximation was good enough for the problem. Second, I made the assumption that this device was in the active mode. Who knows? Yeah. Yeah, so if we made the assumption that we are in the active mode, we know that VBE is going to be about 0.7, but we don't know that VCE, or V out here, has to be 0.4. It could be 0.4, 0.5, or 400. You see? So VCE is not dictated on the transistor in the active mode. Well, let's change things a little bit. Well, so let's try to reason our way out of this. What do you think is happening? What is the problem that caused this? That I got a very, very negative VCE and certainly far below 0.4 volts. What is it that I could have changed in the circuit, or I could change now, to immediately remedy this issue? The assumed what? Assuming it's in the active mode, the collector and emitter current are approximately the same, right? Oh, I got it from the emitter because my base is at 6.66 volts, so my emitter is at around 6 volts, and so I have 6 milliamps. Yeah. What is a change I could make to make things make sense here? Increase the 20 or reduce the 10K. Now, if I increase the 20 volt, then things will change at the base also. So I'm a little uncomfortable with that, right? The resistive division that you have on the left-hand side will also be affected. So let's leave that aside. But what if, instead of 10K, what if I had 0.5 kilo ohm? Then what would the collector voltage be? Would be 0.5 kilo ohms times 6 milliamps. That would be 3 volts below 20, right? the collector voltage would then be 17 volts. And my VCE would then be approximately 11 volts, way in the active mode, no problem. I would still have to verify the assumption that the base current is pretty small. In that case, my base current being 100 times less than 6 milliamps would be 0.06 milliamps. Certainly compared to the current that's going through those two resistors, that was a small current, about 10 times smaller. Not a bad approximation. So if I made that 10K resistor smaller, this thing would more or less work out. Now I want you guys to think about what happens as I do this. If instead of this 10K, we had a variable resistor, okay? Imagine, I'll redraw this because I don't want, let me just point out. First, assuming active mode, and then concluding that this transistor is most definitely not in the active mode, and so a contradiction. Contradicting our assumption. Now let me redraw it with that change. Instead of a 10 kilo ohm, I'll put a variable resistor. Let's call it R. I'll keep everything else the same. 20 kilo ohm, 10 kilo ohm here, 1 kilo ohm here. Everything else the same. Even draw it exactly in the same way. We just did this, talked about having R being half a kilo ohm and how things would work out, and you would indeed be in the active mode. What happens if I start increasing R? Let's say if I have 0.5 kilo ohms, then things are fine. What happens if I increase this to 1 kilo ohm? Well, the voltage here will go down, right? What if I make it 2 kilo ohms? This voltage will go down further. Because, you know, assuming that you have that 6 milliamp current being pulled through here, this voltage will keep going down as you increase this resistor. Now, mind you, again, within our approximation here, you have approximately 6.66 volts. So here you have approximately 6 volts, which gave you the 6 milliamps, okay, which also gave you the 6 milliamps. What do you think happens when I reach, as I keep increasing this resistor R, when I reach a point where this voltage here is around 6.4 volts. What happens? Let's see, first of all, what value of R do I need for that voltage to be around 6.4 volts? 2.2 amp approximately, right? So that's about 14 volts divided by 6 milliamps. You know, maybe a little less than that, right? Let's say 2.1, 2.2 kilo ohms. So what happens if I now put a resistor whose value is higher than that? Will I just have this output voltage go down further? 6.3, 6.2, 5.8. By the time this R has reached, like we had before, 10 kilo ohm, this will be at minus 40. Is this what's going to happen? We kind of felt that was not what was going to happen. So what will happen? If I had 2 kilo ohm here, I would still be safe, right? Because this is 20 minus 12, so that would be 8 volts, right? That's still giving me a collector emitter voltage of about 2 volts. I'm still above saturation. I'm still in active mode. If I made that 3 kilo ohms, then I would be in trouble, because 20 minus 18, my output would be at 2 volts. That's already, my collector emitter voltage there is already showing negative, which shouldn't. So what happens as I keep increasing this resistor? How far will this go down? And what happens beyond that? If this is not what happens, right? As we said, this is a contradiction. It's incorrect. This, in fact, does not happen for a transistor. It goes into saturation. That's exactly what happens. So if it goes into saturation, now let's look at, again, the IV characteristics. Collector current versus collector emitter voltage. So as I increase that resistor R, the collector emitter voltage, was here, 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 kept going here, down, and eventually reached about 0.4 volts. And further increase of R tried to force that to even lower. Now, what do you notice from this curve? As I go into saturation, the collector current starts going down, right? I'm coming to this point, this point, this point, this point, this point, this point. So something interesting is happening here. If I try to put a bigger and bigger resistor there, which will force the collector emitter voltage to go down, the collector emitter voltage will not reach negative, because as you are going down on this curve, the current in the collector becomes smaller and smaller. Your collector emitter voltage is basically playing in this range, 0.4, 0.3. If you really push things too hard, maybe you will get to 0.2. But by then, you will not have much collector current to create a big voltage drop on that resistor R. So now let's see what happens. My base is at 6.66 volts. My emitter is at 6 volts. My emitter current is still 6 milliamps, but the collector current is going down significantly. If it was approximately 6 milliamps before, when I was inactive, same as the emitter current, now it's no longer that, because it keeps going down to smaller and smaller values. How do I get the value of the collector current then? So imagine I say I have a 5 kilo, or let's say the original example. I have a 10 kilo ohm resistor here. What is that collector voltage? And what is the collector current? You see, it's not, that's a very good start. The suggestion is, well, if the current is going to 0, the collector voltage is going to be about 20 volts, right? That's a very good starting point. But if the collector voltage was about 20 volts, this transistor would be very far from saturation. You would have a, right? You wouldn't be in there. Your collector current would be high at 6 milliamps. So it feels like you're trying to go one way, and the transistor reads your mind and does something the opposite. So notice the collector current, well, unless you really get to the origin on that curve, the collector current is actually not 0. It's getting smaller and smaller than 6 milliamps, but it's not 0. So what does happen here? That's exactly what happens. This collector emitter voltage, like I said, will start playing in this range. It will keep going down, but very, very slowly as let's say you go to higher and higher resistance values there. Let's say approximately, let's just approximate things for now, right? Let's say the moment you entered the saturation, at that point, the collector voltage was just 0.4 volts above the emitter voltage, right? So here, you would be at 6.4 volts, right, at the onset of saturation. Now, what is this current? Right? If I know that voltage, 20 minus 6.4, that's 13.6 volts drop across the 10 kilo ohm. That's 1.36 milliamps. So now look, it means on the graph you're somewhere around here. Not at 6 milliamp, but you're somewhere here. Let's say 1.36 milliamps. And your collector emitter voltage is maybe not 0.4, but maybe 0.15 volts, right? I'm just making these numbers up approximately. So yeah, maybe your current wasn't exactly 1.36. It was more like 1.38 or something, right? But see what happened is that as you drove the transistor more and more into saturation, you basically kind of didn't manage to decrease the voltage on the collector very much. And the current of the collector essentially saturated at somewhere around 1.36 milliamps. Now, all of this is with the assumption that nothing has changed in the emitter voltage and in the base voltage, right? I haven't revisited that. But to a first approximation, this is what's happening. This transistor is driven into saturation, and it has that kind of current at the collector. So again, to a very first order type of approximation. Recall again that a single curve like this corresponds to a single value of VBE. So in practice, maybe VBE is also changing in this process, which could make my point go from a curve like this maybe to another curve, slightly different. But again, to first order, not a big deal. If we say that this is a qualitatively correct solution of this problem, do we leave it here? Or is there something else to do? Yeah, this is what I meant, that if you want to be accurate now, you have to say, actually, it wasn't really 0.4. Maybe it was 0.15. So this would be more like 6.15, right? And so that current is maybe 1.38 or 39, right? That's kind of rough. This is very, very crude, right? But you would agree that that wouldn't change things too much, right? But yeah, very good point. But is there something major here? Something really major that I have now forgotten? Well, remember when we started challenging our first solution, we said there were two things there that we had done. One was the assumption that it was active, which now we saw had to be challenged. The other thing that we had done there was neglecting something. What was it that we neglected at the very beginning of that solution? We started by assuming that the base current was 0, right? What is the base current here? Can we still assume that it's 0? Well, so far we have assumed, but I'm asking if that's valid and or whether that assumption should be challenged or not. Yeah, but we said that current is beta times less than the collector and emitter current. So let's say if you divide 6 milliamps by 100, you would get 0.06 milliamps. That's pretty negligible compared to the current in those resistors. Is that correct here? Well, what is the base current? Give me a number here on this graph, IB. Don't forget KVL and KCL. You know, it's something that you know, every other thought that you have in your mind is a reminder to yourself. It should be of KVL or KCL. What does KCL say? What is IB? 6 milliamps minus 1.36 milliamps. Now that's 4.64 milliamps. What was the current we had said approximately I had here? Was it 66 milliamps? And my base current now is hardly negligible compared to that. It's almost 8 times that. So what do I do now? Well, first of all, what happened? This is clearly not beta times smaller than the collector or emitter current. What happened? Yeah, like we said before, you know, that this, and look at that keyword that I slipped in there. Beta is 100 if you're in the active mode. Once you get into saturation, even though this problem, you know, increasing the resistor R to first degree doesn't have an effect in the emitter current, but we saw that it could surely affect the collector current. And that's the point where the collector current cannot keep up with the emitter current anymore. And the difference has to come from base. And in fact, that's the base. That's when your base collector diode is becoming forward biased, and it's starting to have a current. And that current is now sent through the base. Yesterday, you had a question about what happens in saturation and what the form of the curve is. And I said, it's like you have 2 diodes now, 2 exponentials that are subtracted from each other. This is what's happening. Now you have a substantial base current. And in this case, hardly negligible compared to what those resistors would have had there not been this connection. So this also suggests that my numbers might be horribly off. This is not at all negligible. And this is by KCL, let's remind ourselves. Okay. So far, we've spent a lot of time on this problem without finding the solution yet. But what we have seen is exactly how a circuit designer thinks when they see a problem about this. And this is what I want you guys to see and the way I want you guys to think about. Now we'll talk about, of course, how to find the answer. But and of course, this took some time. But once you get used to things like this analysis should take you 5 minutes to get a first-degree feel for what the circuit is doing. And in this case, it seems like the circuit is in saturation. Quite possibly, the current beta, the base current is not negligible. And so you don't have a simple voltage division there because you have those different currents. Let's try again very quickly now to see how we can actually get the numbers then. So my third attempt. This was 10 kilo ohm. Now I know that I should not assume that this is negligible. Let's keep it there. I'll call this I1, I2, and this was 20 volts. IE, IC. Now I'm in saturation, and I know the things that I do know for this third attempt. And again, I'm applying some approximations here. Of course, you could do things much more accurately, but approximations that are qualitatively valid in this case. I'm in saturation. My VBE is approximately 0.7 volts. My VCE is also approximately known, 0.4 volts, or you might say 0.3 volts or 0.2 volts, depending on where we are on that curve, right? But I think you would agree that compared to that 20 volt difference that we have there, 0.1 or 0.2 volts more or less on that VCE does not make a big difference. Okay? Now, what are the things that I know? Let's call this, I'll go with node voltages, VB, VC, and VE. Okay? Let's write the equations. First of all, VB is simply 20 minus 20K I1. And I will use milliamps for the units of current, so I don't need to carry that kilo there. Okay? That's VB. VE is VB minus 0.7. I also know that VB itself, it can be written also as, let's write it here also. VB can also be written as 10 times I2 going up from ground. What else do I know? I know that VE also can be written as 1K times IE, right? I know that VC can be written as 20 minus 10K IC. And I also know that VCE, which is VC minus VE, is approximately 0.4 volts. And finally, my KCL also, that IB plus IC is IE. I think I have everything here. Let's see how many equations and how many unknowns we have. We have VB, VE, and VC. That's 3 unknowns. And then we have 5 currents. That's 8 unknowns. How many equations do I have, and have I missed anything? So I want to leave you guys with this for a moment to review while we take a short break also, and see if you're happy with solving this or if there's something missing. Or say again? Ah, very good. You're saying we have 8, we said 8 unknowns, right? Yeah. But I've written 7 equations. I mean, these 2 I have already implemented in my equations, right? So yeah, this is where things start. So yes, which equation are we lacking? The other KCL. The other KCL, very good. I1 was I2 plus IB, yeah, right? Happy with this? Now, if you solve this, what do you expect the solution will be? Do you expect the solution to be close to this? This is a very important question that I want you guys to go home and think about. Well, first of all, verify the equations to make sure everything is correct and complete, that I have not missed any equation, because maybe I have duplicated an equation in a different form and I'm still missing an equation or something. You should go and verify these. But assuming that the equations are correct, approximately, and you solve it, do you expect the solution to be close to this or drastically different? And if drastically different, in which direction? For instance, do you expect to get a higher or lower emitter voltage than this? The question then is for you to think about these trends before actually punching in the numbers and getting the answer. Okay? That would be a very useful exercise. Please try that at home. Well, you see, I've assumed that we are in the saturation region, right? I put VC equal 0.4 volts. Yeah, or again, you could say, if I'm deeper into saturation, maybe that 0.4 is 0.3, right? It's not going to make a huge difference here. Why? Because the voltage drop I have available to me is 20 volts. If 0.4 volts is taken by the collector-emitter difference, or 0.3 or 0.2, it's not going to make a huge difference to the voltage drop across the 10 kilo ohm and the 1 kilo ohm resistor. Again, I'd like to emphasize this is a very important problem. Try to think about, if you solve this, whether you're going to get things that are close to this, in which, of course, there is the question of whether you are in saturation, right? Or if you do things now very accurately, whether you're going to end up in the active mode here. You should really think of this problem and this type of analysis as almost like workout, right? That you need to get into this type of sport, this type of activity, right? This is the nature of this activity, that you need to be able to do this kind of analysis. And it's better to try this on the sample circuit, on something like this, from different points of view in steps like this. So this is a very, very important exercise to do. I want to leave you with that to do a little bit on your own. And of course, I'd be happy to talk about it in the office hours, or if you want to ask things about it next time. But it's important that you guys spend some time. Let's do another example for a change. Take this circuit. Let's do a PNP transistor. Again, assume a beta of 100 in active. Let's try. Let me call this IC, IB, IE. Where should I start? KVLs and KCLs, very good. What's the next step? Or by the way, when I say KVL and KCL, obviously a nodal approach or a mesh approach are included in that, right? Like in the previous example, we were using more of a node representation. Should I start by assuming that the base current is negligible? Should I start assuming that the device is active or in saturation or off? what does your intuition tell you? Is this device going to be off saturation, in saturation or active? It's a PNP transistor. If the currents are in the direction that I have shown, now that's the direction of the convention for the currents for the PNP transistor. If the currents are really positive numbers, so that is indeed their actual direction, would this device be active or saturated? It would be active because the current IB going through that 1 kilo ohm resistor creates a voltage drop from the base to the collector. There is that drop, 1 kilo ohm times IB. So the base collector voltage is positive, if IB is positive, which means you are inactive, right? And if you wanted to double check the emitter collector voltage, yeah, you would have the 0.7 volts across from the emitter to the base, and then another drop across that resistor from the base to the collector. Therefore, it appears that this device wants to be in the active mode. Now, let's see if we can find a consistent set of numbers that would correspond to a solution for the active mode. Would it be a good assumption to neglect the base current if the device is in the active mode? The base current would be 100 times less than the emitter current, or 101 times less than the emitter current. Would it be logical to neglect it here? Well, let's see. If I neglect the base current, what does that tell me about the base collector voltage? As a first approximation, what happens if I neglect IB? Then I conclude that the voltage between the base and collector, VBC, this voltage, is approximately 0, right? What does that tell me for IC and IB? IE. What is this voltage drop? IC and IE would be approximately equal to 10 minus 10 divided by, minus the VCE divided by 1K plus 2K, right? And if VBC is approximately 0, VCE would be approximately 0.7 volts, right? Or, this is VEC, the way I've indicated it. You see, it's very easy to make mistakes when you go from one transistor to another, VEC. So VEC is approximately VEB, which is 0.7 volts. This number would be then 19.3 divided by 3, 6.4, let's say, approximately. Was the assumption of neglecting IB justified? This is 0.064 milliamps. And so if I want to double check what my actual VBC is, that's approximately 1K times 0.064 milli, which is 0.064 volts. This assumption of 0 for that is not too bad an approximation in this case. Well, if IB is 0, VBC is IB times 1K, right? Hold on. I'm sorry, I have mislabeled this, consistent with my other mistakes constantly. But yeah, they're almost equal. Yeah, so we see that the approximation that IB was negligible and VBC was approximately 0 turned out to be not too bad, because all that means is if I make this correction and if I put it in the equation where I got the current through the collector and emitter, it doesn't make a whole lot of difference, because that's an amount subtracted from 20 volts. So not too bad an approximation. But now imagine you want to do it accurately. Let's not neglect IB. Let's write the equations. I have the voltages labeled like that, and the currents. What are the things that I know? I know that VEC is VEB plus VBC, right? That means VEC is approximately 0.7 volts plus VBC. VBC itself is 1K times IB. Again, I'll use milliamp for the current, so I don't need to carry the K. Now, what about the emitter and collector voltages themselves? If I wanted to directly work with VEC, VEC is the 20 volts that I have there minus 1K times IE minus 2K times this current, right? Let's call this I1, right? I can write it like this. VEC is the 20 volts minus 1K times IE. That's the voltage drop there, minus 2K times I1. And I also have the KCL that tells me IB plus IC is I1. And I also have the transistor relationship with a beta of 100. IC is 100 times IB. Let's see if we have enough here. Unknowns are VEC, VBC, IB, IC, and I1, right? That's 5 and 5 equations. It looks like I haven't forgotten anything, but again, to be verified by you guys. Now, if you solve this, again, go home and try to solve this, but before doing so, try to think about whether you expect the solution of this to give you something dramatically different from what we got from this assumption. Well, this was an NPN transistor, so the base emitter voltage was about 0.7 volts. This is a PNP transistor, so it's the emitter base voltage that's about 0.7 volts. The polarities are reversed. And you could, basically any circuit that you can make with one, you can make the reverse polarities with the other one with the same numbers, right? Let's do another example. I want to make a connection to something we saw in the past. Remember, we talked about the DC voltage source. We started from an AC, we did rectification, filtering, and finally we put a regulator at the output. And we had a circuit like this for the regulator. Right? And then you put your load resistor here. We did some examples of this. And the job of that Zener diode there was to keep the voltage there more or less constant, even if you change this load resistor. Even if you change this, which meant then you had different requirements for the load current, the job of the Zener diode was to take the variations in the current and do so even as your input here maybe had some ripple. Right? And keep the output more or less constant. That was the job of the regulator. And the challenge of this regulator was precisely that, to do its job properly. Namely, if I made a big change in this load resistor, well, if this current IL had a big change, then what would happen? At some point, the Zener would be forced to go outside its range. Either its current would become too low, it would go below the knee current, and its voltage wouldn't be able to stay around the Zener voltage anymore, so you would lose the regulation functionality. Or you would end up with a current in it that's too high, the Zener diode would be damaged, too much power dissipation in it, right? So yes, it could do this, but for a range, the power limit, yeah. No, we're talking about the reverse. The Zener is being operated in its reverse mode, in the breakdown mode. Yes. Well, that's the point, that if this is your Zener mode, and if you greatly change the demand for IL by changing RL, you could end up either going too far here, so that's too much power, or you could end up going here, because if you require too much IL, there won't be enough left for the Zener, so you would go there, you would lose the voltage regulation. Okay? So it is a challenging task on the Zener, and it could do it within a certain range of variations of RL, but that range has limitations, and we did some examples of that. Now look at this circuit. Think about what this does. So this is another example. Let's make it more quantitative. Assume that this input is varying between 10 volts and 11 volts. Assume that this is 1 kilo ohm. Assume that in reverse breakdown, in the Zener mode, the diode can be represented by a constant voltage. Voltage of, let's say, 8 volts. Okay, and also, and that the knee current for this, meaning the current beyond which you are in the Zener mode, is 1 milliamp, and the max current that it can handle, IZ max, is 10 milliamps. Okay. Now let's put a number here also. Let's also assume that it's the same connection here, the same 10 volt to 11 volt source connected there. Okay. And imagine this here, this load, for now, let's assume it's 10 kilo ohms. Assume that your MOSFET, the N-channel MOSFET, has a threshold voltage VT of 2 volts, and the value of WL mu C aux for it is 1 milliamp per volt squared. Find V out. Let's see if we can start by making an important observation. And this is, by the way, again, it goes back to the general way of thinking about electronic circuits. You know, if you start stacking things and having more than 1 or 2 or 3 devices connected, it could become a daunting task to analyze the circuit. And if you think about the fact that your computer has billions of transistors in one circuit, you know, imagine having to solve a circuit that has billions and tens of billions of transistors. Write all your KVLs and KCLs. Do you think that's how a computer architect approaches things? Oh, you know, I need this functionality. I'll just put a billion transistors like that. It's not like that. It's very hierarchical, right? Because these, there are modules that work within ranges of input and output in such a way that you can analyze them independently and then connect them to something else that does something else. Like the way we talked about cascading op-amps and op-amp circuits. Here you have 2 things that are kind of more or less familiar. The left-hand side is a regulator circuit. The right-hand side is a simple connection of an N-channel MOSFET with a resistor. In terms of the simplicity, kind of like what the previous examples were, even simpler. If these 2 sides were more or less decoupled, it would be relatively easy to analyze. Now, let me see if that is justified. For a moment, let's think about the fact that the MOSFET in DC steady state does not draw current into its gate, right? The gate current in DC steady state is 0 for the MOSFET. Now, is this problem in DC steady state? No, because the input voltage is varying. Now, the variations, you might say, are small, right, between 10 and 11 volts. So that does not represent a very high AC signal. It's almost a DC steady state plus some ripple on top of it, right? But you might say there is a small set of variations. Now, let me then again invoke that the kind of circuit engineer type of look into this. If for a moment I assumed that this was in DC steady state, and I said the gate current was 0. And again, we'll question this assumption for now. But if I assume that, what can I say about the voltage here? 8 volts. That's the Zener voltage. As the input changes from 10 volts to 11 volts, does that 8 volts voltage change? No, the Zener is modeled. We've taken a simple view of the Zener. What we are saying, in effect, is that the breakdown of the Zener is extremely sharp, almost vertical, right? So the incremental resistance there is negligible. And we can assume that that's 8 volts. Now, let's make sure that the Zener stays in the Zener mode, right? What is this current? Well, if you have an input of 10 volts, that current would be 2 milliamps. That's above the knee current, right? The knee current is 1 milliamp. So you're good. You're in Zener mode. If your input goes to 11 volts, that current will become 3 milliamps. And yeah, that's obviously still above the knee current. It's also less than the max. So the Zener is happy. So indeed, this Zener will keep that voltage pinned to 8 volts there. Which means then, for the MOSFET type of the circuit, in fact, it is in DC, right? The MOSFET does not see any voltage variations there. Because the voltage there is pinned at 8 volts. And it kind of isolates the MOSFET from seeing variations that are due to the variations at the input. Now, that's very good. It means, because all that current is going through the Zener without the Zener changing its voltage. Now, if you know that, find V out. How do we find V out? We know the gate voltage, 8 volts. V out is just the source voltage, right? Is this device going to be in saturation or triode? Now remember, saturation here is what in the BJT we called active. This is going to be in saturation. Why? Because whether you are in saturation or triode, it goes back to this curve, right? It has to do with whether the, now this V out, for instance, in this case would be your drain source voltage, right? If that drain source voltage is positive, you would be in saturation, which is the equivalent of the active mode. If it's greater than a certain threshold. Let's assume that that is the case. Okay? Assume that, start by assuming that you are in saturation, which means your VDS is greater than VGS minus VT. If you are in saturation, then the current, we call this IS, which is the same as ID. The current is this, right? But at the same time, I know that the gate voltage is 8 volts, and VGS is that gate voltage minus the output voltage. Right? And at the same time, I know that V out is 10K times IS. And IS is the same as ID by KCL. So it became pretty simple, right? If we replace things, ID equals half of 1 milliamp per volt squared times 8 minus V out, which is my VGS, minus VT, which we said is 2. Right? But V out itself is 10 ID, so I can maybe just directly replace. Now we can calculate ID from here, or IS, and from that get V out. Now here is a question I want to leave you guys with. Solve for ID and V out, and verify, first of all, whether this is correct. And we are in the saturation mode. Solve this. Then do another problem. So if we are not in saturation, if we are in triode, then solve it again. Then do another problem where you change that resistor, the load resistor, to something different. Try 5K and 15K. Okay? And finally, then try again by replacing the MOSFET with an NPN BJT. All the same problem with a beta of 100. And again, do the same problem. Now you see that this equation is not very difficult to solve, right? It's just a quadratic equation. Try this and see what you observe, how things change with the values of these resistors, how things change if you change the transistor, right? Again, these are all really examples of dealing with transistors in DC. And there are many, many, many other examples one could do. But hopefully this will start getting you in the mindset. OK, thank you.